just being honest, sometimes the problems you're asked to solve as a physics student seem contrived. And this is one of those situations where you might have two objects hung over pulleys connected to a low friction cart, and you're asked to find something like the acceleration of the system as a whole, or the acceleration of a part of the system, or maybe how much tension is either in the left string or the right string. And to top that off, you might also be asked to solve that in a symbolic way, so you're finding expressions which represent the acceleration, or a symbolic expression which represents the tension. In this video, I want to walk you through this kind of convoluted situation and do that. Find symbolic solutions for the acceleration of this system and the tension in the left string. So let's find the acceleration first. Whenever you're given a complicated system like this and you want to find the acceleration, I would define the system as the entire thing. Whenever you're defining the system, you can define the system however you want, but sometimes it'll be more helpful to define it one way versus another way. So when finding the acceleration, let's define the system as everything: object A, object B, and object C. And what's given is that object A has mass m, object B has mass 6m, and we're going to not consider friction between the cart and this horizontal table. And this other hanging mass has mass 3m. So when we find the acceleration of a system, we just use Newton's second law. So if we can find the sum of all the forces on the system, divide by the total mass of that system, that will give us the acceleration of the system. So let's just start substituting things in we know for these two terms to get a final expression for the acceleration. And we're only going to express our answer in terms of m and any physical constants, like the gravitational field strength of the Earth. Before we find an expression for the sum of the forces on the system, let's just think about what this system would do. This hanging mass is 3 times larger than this one, and so gravity's going to be pulling on it with more force. So this whole system is going to tend to accelerate in this direction. So let's define the positive direction as the direction that each part of the system is speeding up in, as indicated by this red arrow. So there's a gravitational force pulling down on object A, and there's a tension force pulling up. And if this object A is speeding up in the upwards direction, the tension pulling up must be greater than the gravity pulling down. And if there's tension in this side of the string, there's also tension in this side of the string, and they're the same size tension, because we're going to assume that this pulley is an ideal pulley, which means it's negligible mass and negligible friction. Well, looking at object B, it's also feeling gravitational pull downwards, and the table's being compressed, so it's pushing back up with a normal force. Object B is also being pulled to the right with a tension force, and that same tension force will be pulling up then on object C, and object C itself is also feeling a gravitational force down. So the question is, what do we plug in for the sum of the forces on the system? Before we just add up all 8 forces, let's think through if any of the forces cancel each other out. These two tension forces are the same size, and this tension on object A is trying to speed up the system, and this tension is trying to slow down the system, so they cancel each other out. And then we have the gravitational force pulling down on object B and the normal force pushing up, and this car is just speeding up to the right. There's no acceleration in this vertical direction, so these two forces have to be the same size and cancel each other out, so we don't include those. And then lastly, these two tension forces would also cancel each other out, because this force of tension on object B is trying to speed up the system. This force of tension on object C is trying to slow down the system, and if they're the same size, they cancel each other out. So the only two forces left over on the entire system that aren't canceled out by something else would be the force of gravity on object C and the force of gravity on object A. So let's expand our expression for Newton's second law. The sum of the forces on the system is just the force of gravity on object C plus the force of gravity on object A. And we're going to leave the little vector notation over the top of that to remind us that these two expressions, or these two terms, could be positive or negative. And we'll deal with that in the next step. And what's the mass, the total mass of the system that's being accelerated, where the velocity is changing? Well, it's the entire system as we defined it. So it's mass A plus mass B plus mass C. So now we can't quite leave this. This is a symbolic expression which represents the acceleration, but it's not only in terms of m and any physical constant. So let's deal with the numerator first. How do we think through the size of the force of gravity on any object? Well, remember, the force of gravity on any object is equal to the mass of the object times the Earth's gravitational field strength. Precisely, it's about 9.8 newtons for each kilogram. That's G, the Earth's gravitational field strength. But if we were solving quantitative problems, 10 newtons per kilogram would be good enough. But we're not plugging a value in for G. We're just leaving G as G so we can have a symbolic expression. So the force of gravity, let's say on object C, is 3m, that's its mass, times G. And this force of gravity is trying to speed up the system in the positive direction that we defined. So positive 3mg represents, it's a symbolic expression for the size of the gravitational pull on object C that has mass 3m. And the force of gravity on object A, that's in the negative direction that we've defined because it's trying to slow down the system or decrease its speed. And so we're going to subtract a symbolic expression which represents the size of gravity on it. And so we just take the mass of that object, which is m, times the gravitational field strength. So minus mg represents the force of gravity on object A in the negative direction. And then mass A, mass B, and mass C. Let's plug in what's given. So the mass A is just m, the mass of object B is 6m, and the mass of object C is 3m. So the total mass of the system is m plus 6m plus 3m. So let's just simplify. We're almost done. So we have positive 3mg minus mg, which means in the numerator we get 2mg, and then m plus 6m plus 3m gets 10m. And so we're almost done. We could leave it as this, or let's just simplify. We've got an m in the numerator and m in the denominator, and so those cancel each other out. And 2 divided by 10 is the same as 1 over 5. And so our simplified expression is just g over 5. The acceleration of the system is just the gravitational field strength of the Earth divided by 5. And that's all allowed because we can express our answer in terms of m and any physical constants. And in our answer, m ended up just canceling out, so we don't even have to include it, and we've got our gravitational field strength constant. So the acceleration of the entire system, a symbolic expression for that, is just g over 5, and that also represents the acceleration of any part of the system. So that's A's acceleration, B's acceleration, and C's acceleration. So now let's use that information, or that symbolic expression, to come up with an expression for the size of tension in this left spring. So in order to do this, let's change our system definition to just define the system as object A. So this whole thing is speeding up with an acceleration of g over 5, and so A also has an acceleration of g over 5. So let's use Newton's second law again, but we're only going to plug in expressions that represent what's true about object A. So it's the acceleration of object A is equal to the sum of all the forces on object A divided by just the mass of object A, because Newton's second law can apply to a system of objects or just an individual object. It just depends how we're defining the system. And so what are the two forces that we're adding together on object A, which is causing its acceleration? We just have the force of tension pulling in the positive direction that we defined, and the force of gravity pulling in the negative direction. Or we're adding together tension on A plus the force of gravity on A, and we're dividing by the mass of A. And we know the mass of A, that's just mass m. We know the acceleration of A, that's the same as the acceleration of the system, that's g over 5. And so let's just keep plugging things in and solving for the tension of A. So for our next step, let's plug in the A's acceleration, which is just g over 5. We've already determined that for the system, so that's the same for object A. And then the force of tension is pulling in the positive direction, so we're just going to have positive Ft. And the force of gravity on A is pulling in the negative direction, so we're going to have a negative sign. And the symbolic expression, which we've already talked about, which represents the size of the pull of gravity on object A, is just equal to its mass times the gravitational field strength. So it's minus mg. And then what's A's mass? Well, that's what's given. It's just m. So we're dividing by m. So all we need to do now is solve this algebraically for the force of tension, which just means we're going to move everything over on the other side of the equal sign. So we just have Ft equals something. and whatever's on the other side of that equal sign is our symbolic expression. So we've got one fraction equal to another fraction. I'm going to make it a little bit simpler. I'm going to cross multiply, so I'm going to multiply m by each side, effectively moving it over to the left side, and then multiply this by 5, canceling it out, and so it ends up moving it over here. So if we cross multiply, we get on the left side m times g is equal to 5 times ft minus fg. So we have to multiply each part times 5. So we have 5 times the force of tension minus 5 times mg. So let's first add 5 mg to the right side, which is going to cancel out the negative 5 mg. So we have to add 5 mg to the left side. And we get, on the left side, 6 mg equals just 5 times the force of tension. All we need to do now is just divide each side by 5 to get the force of tension equal to some expression. When we do that, we get that tension is just equal to 6 divided by 5, or 6/5 times mg. And this is a symbolic expression which represents the size of tension, and it's only in terms of m and any physical constants. We've got m and g right there. I hope this has been helpful.